All right. So let me share my screen here. So the basics of taping and leveling as it relates to field applications are as follows. So taping, this is our horizontal control. And what do we use? We use steel tape. And who can tell me what issues or corrections we have to think about when we use steel tape in order to measure a distance? So you can imagine, like, here's a piece of land from the side. Here's point A. Here's point B. You have a person at A and a person at B, and you're gonna pull some tape. What do we have to think about?
There are
This-
four. Oh, go ahead.
I was going to say, you got the sag in the middle there.
Yep, so we got sag.
Pull.
Yep, pull. Temperature.
And then length as well.
What was that?
Oh, length.
And length. So I've drawn an exaggerated version here, but as you can see, that you have to correct. Sag is a big one, and you can imagine that if you have a sag here and you read your measurement here, will your reading be larger than what's real or smaller than what's real?
Larger.
Yeah, it'll be larger than what's real, exactly. So that's the big one. And for this reason, we try to keep our steel taping in shorter sections. It's easier to eliminate these sag. So when it comes to doing this in the field, in order to, if we either have too long of a distance, or let's imagine that AB was on a incline, we're gonna actually do multiple taping sections, and we're gonna break tape and mark the ground in between with pins. That's pretty much it. But in our lab, we're not going to be doing any corrections because you want your precision before corrections to fall within a certain tolerance. You only do corrections after the fact in order to really, really sharpen your pencil, is the colloquial term. So let's go to our actual traverse. Let's see if I can find, here we go. Cool. So can you see my screen? Can you see Cabrillo?
Yes.
Great. So here we are, the Cabrillo library. And zoom out here. Here's the engineering building. and right over here is where all of our serving equipment is stored. We'd grab it, we'd come out to the the amphitheater area, the area in front of the library, and we place our guineas and tacks in the ground. So the area that we're going to be looking at today, the triangle that I drew a lovely, lovely version of in the notes, is actually on this grassy area on the, I guess this would be the western side in front of the library. So the southwest lawn of the library. So for reference, there's some drainage in a manhole up in this area. You can't see it here, but that's where that manhole was that I described in the videos. And then the pins A, B, and C are located approximately here. That'd be A, approximately here, be B, and then down this little slope here is C. So that's approximately where we are looking at for both our taping and differential leveling lab. So just want to give you an overview of the area, and then we'll come back to the lab book now. Cool. So that is ABC. And that's on the southwest side of the library lawn. So what do we still need to do in our lab books? We need to describe the location, right? So what aspects do we still need to add to our lab book now? What's missing from the right-hand side?
Weather.
Weather, yep. That's important for steel taping.
Names of the party.
Names, date, and location. Exactly. So make sure we add the date. It's the 26th, 2020. Our location, and the location of our survey is the southwest lawn, Cabrillo Library. And the weather, well, this is less relevant for us because this is old data, but I think that, usually if we get there Saturday morning, 9 o'clock, it's usually foggy and just under 70. So let's pretend. Great. Somebody also mentioned the north arrow. So that's perfect. Let's add a few more notes in our in this little drawing here, because it's kind of hard to see exactly where we are. So we know if we're in front of the library, you have the walkway kind of over here, and that walkway comes down here. So let's just add a little note. You have a walkway there. And a walkway here. And some stairs, right? Because this is sloping down. And then the library is kind of up here. This isn't to scale, it's just kind of give you an idea of where things are. And then the north arrow, of course. Now I think that in this one, north would be about there. And our favorite thing that we want to add to all of our notes is NTS, not to scale. This is just a very general look at where we are. And then for our names, you can just write your name. So Kyle O, and then ENGR1A class. We're doing this all together. Cool. So that's that. That's where we exist in space. Now let's look at some of the measurements we're going to do. So the first one is line AB. So line AB, right there. And when we taped line AB, it was actually done in 2 sections because it was too long to do with a single 100-foot steel tape. So the first section was taped as 60.000 feet. Usually when you see a measurement like that, it's somebody who intentionally taped exactly that distance. So it doesn't mean it's wrong, it just means that somebody intentionally did it that way. And on the back measurement, because remember, you do it one way, then you switch positions, and then you go B to A. It was measured as 60.005 feet. Now, what happens then is that we had to break tape approximately here. And we had to measure from our point of breaking tape to B. So when we did that, that was 61.010 feet on the forward measurement and 61.008 feet on the backwards measurement. Now to get the full line AB, we'll have to sum those measurements. So what is the sum of our forward measurements? Can someone do that math for me?
$121.010.
Exactly. And the way you reported it is exactly what we want to do. Make sure you don't lose that last significant digit, even though it's a 0. And on the back,
$121.013.
excellent. So for all of these, we want to make sure that our measurements are within precision, or else we'd have to go back and retape it. So you don't want to do this. You want to do this when you're in the field. You don't want to get back to the office, do your calculations, and realize that you're not within tolerance. So we would do this precision calculation in the field. And we have to do it from A to the point of breaking tape. So that would be this first line. We have to do it from breaking tape to B, and we need to do it for the entire section. So in order to do our precision measurement, we have our precision equation down at the bottom, just a sample calculation of how that's calculated. So what would be the precision, or before I get there even, let's take a step back. What's the average distance on that first line that we taped?
$60.0025.
Exactly. Now, we are reporting an extra digit here, but we're just reporting that for the sake of math. We don't actually think that we have that level of precision from our instruments. That's just in order to use that in our calculation. So given an average and our two measurements, forward and backwards, can somebody calculate the precision for me in terms of 1 over x? And once you have that calculated, if someone could just write it in the chat. One to 12,000. That's what I calculated as well. Is everybody else seeing how we get that value, or do you want me to, Phil, you're confirming? Not seeing it. Okay, so that's fine. Let's do the precision calculation and for this one, because once you see it, it's not too complicated. But there we go. It is a little tricky. Precision for taping. Okay, so we have two measurements. We have a forward and a backward measurement. So in our precision, is equal to the absolute value of our forward minus our backwards. Oops, that should be an absolute value sign. So those are absolute values, and divided by the average. Oh man, spelling is hard. So we have our forward measurement, which is 60.000 feet, minus our backwards measurement, 60.005 feet, absolute value that, divided by the average of the two, 60.0025 feet. Now, when you do that calculation, if you plug that into your calculator, what do you get? You don't get 1 over 12,000. You don't see 12,000. What you get is something like this. 0, 0, 0, 0, 8, 3, 3, 3, and so on. So, but we want to know what that error represents in physical terms. How many inches, meters, feet of error do we have per X number of feet? So we don't want this. This is confusing. It doesn't really tell us anything. So in order to get that in terms of 1 over X, all we have to do in our calculator is do a little 1 divided by answer. And that gives us our denominator. So when I do that calculation in my calculator right now, 1 divided by, I have a Texas Instruments 30X, so it'll be slightly different, but normally what you can do is you can recall that the last answer you got, so 1 over answer, and you get 12,000. So the precision is 1 in 12,000. And in this case, our measurements were in feet. So if you want to be even more clear about what that precision is, that means that we expect 1 foot of error every 12,000 feet. So if we went out and taped 12,000 feet, we expect that we're going to be off by a foot. Does that kind of make sense to people? Cool.
Yeah, that does make sense. Thank you.
Excellent. And just like as a sanity check here, 12,000 feet is a little over 2 miles. So that means that if we were like laying something out horizontally over 2 miles, we would have like a whole foot gap. So you can see why this is important, like especially if you're doing, like if you've ever driven Highway 1 and there's a ton of bridges, you can kind of get a sense of why this is important to have really tight tolerances. Like you don't want to pave a couple miles and then have like a gap between your bridge deck and the pavement. So things to keep in mind. Great. Thank you for asking questions. I appreciate it. So let's report that. So that would be 1 in 12, 1, 2, 3. All right, so you can do the same for the second measurement on AB, and you can do the same for the sum measurement on AB. So if everyone can pull out their calculators and do the averages and precisions for each of those, that would be great. And then we will get to line BC.
Kyle, we lost your screen.
Oh, sorry about that. One moment.
Should we be writing all this in our books now, or is it okay to do everything in pencil and then put it in pen in the book later?
So this should be done in your field book in pen. Um, you're welcome to like turn to another page. Like you can save the page after this for some calculations if you want a little bit of room to write out your calcs. So normally I would, if this was real life, I would just turn the page and I would just say lab to continued. And then if I wanted to actually write out all my calculations, I would do it here. Thanks for pointing that out. That's a good point that your first page should be the like kind of summary of everything we're doing in the lab. But it can be hard to do all of the calculations without a little bit of space. So just turn to your next page and have plenty of room for your calculations. Does everybody need a little more time to do the precision calculations, or you want to check back in and see what everyone got?
I just need like a minute of time to go finish. But
Sounds good. We'll give everyone a few more minutes. All right, let's check in on this one. Let's see what's what. So for the second portion of line AB, the average, you can do this one in your head because the forward and backward measurements are plus or minus 0.001 feet. So the average is just in between those. It'll be 60.0, oh, wow, 61, sorry. So what I would do is I would draw a line through that and just rewrite it. 61.009.
I'm sorry, we are looking at the wrong page on the screen right now. We don't see, we can't see what you're doing, the calculations.
No, we can see it. Are you?
Okay,
watching?
maybe mine is frozen, I don't know, sorry.
Am I on the taping page? Can everyone see it?
You're on the tape.
Inside, yes, cool, okay.
Okay, sorry.
Oh, no worries. Always good to make sure Zoom is working correctly. Great. And then, yeah, so if you make a mistake like that, just cross it out like I did. And then the next one, I got 121.012 feet. Everyone got similar averages? By similar, I really mean the exact same, or did I mess up?
I got what you got, so you're good.
Lovely. Okay, so precision. Can someone who has not answered yet tell me the precision they got for the second portion of line AB? So that would be right here. One in 30,504. All right. And as you can tell up here, I actually put the precision in the wrong place. So I can just draw a little arrow and say that goes there. So yeah, that one is 130,504. And what about for the entire line? The sum. Excellent. 1 in 4337. All right. And the last question is this acceptable? What's our allowable precision for this lab? Does anyone remember from our pre-lab videos?
Yeah, I kind of remember. So it's only two measurements, and then we're taking the sum. So that'll be thanks, Elon. Yeah. Elon put something in the chat with.
Yeah, so 1 in 1,000 is that's what we're just specifying for this particular project. So for a very small project, like what this is, 1 in 1,000 for horizontal measurements is going to be what we're shooting for. And all of these are smaller than 1 in 1,000, so we are good. We do not have to go back and retape the line. But you were mentioning, I think that maybe you're getting at looking at the number of setups. That's going to be in our next lab. So for horizontal taping, it's just some specified amount based on the project.
Right.
I'm sorry, can you show how to do precision one more time? I'm getting like totally different numbers and they're wrong and I don't know what I'm doing wrong here.
Oh, no worries.
Sorry.
So here is kind of the walk down. We have two measurements, forward and back. So our precision is going to be reported as 1 part in however, 1 part in X. And all it is an average. It's the difference between the forward measurement and the backwards measurement. And we only care about the absolute value. It doesn't matter if we're too large or too small, divided by the average. So, here's the calculation for the first measurement. Let's do calculation for the next one. So precision for the second portion would be 61.010 feet minus 61.008 feet, absolute value, over the average, 61.009 feet. Now, when you plug that into your calculator, this is kind of the tricky part.
I think that's the part I'm not doing right. I think I'm just like using the calculator in the wrong way. Thank you.
Okay, well, so the tricky part here is that your calculator is going to give you a decimal. That's going to be like
What did you get for the decimal? How many zeros did you get for the decimal?
let's see.
I want to see if I got the decimal part right and I was converting in the wrong way. 7 zeros is what I got. 7 zeros and 3.
I think that, yeah, maybe your order of magnitude is off here because I'm getting 0.0003278.
Yeah.
And then 1 over that.
Okay, thank you. I got the decimal part wrong somehow. Thank you.
Okay, yep. No worries. All right, cool beans. So we're within our 1 in 1,000. We're in the tens of thousands, so that's really good. One thing that this is precision, not accuracy. Does anybody remember the difference between the two in a general sense?
Accuracy is how close you are to the actual value. Precision is how close the values, different values are to each other.
Yeah. Yeah. So it's very possible that we're doing something systematically wrong and getting, we're getting a really good precision here. That means that we're at least taping the same way, but it could mean that we're still messing up. So just keep that in mind. It's always a good thing to keep in mind doing any kind of field or lab work. All right, so let's get to line BC. So BC, we again had to break tape on this one. If you're familiar with that area in front of the library, you get a little bit of a slope as you go down the walkway. We had to break tape. So again, we're going to have 2 measurements. And what those measurements are, BC, the first one is 58.0 0.000. Again, what does that mean? It means that we intentionally taped 58 feet. And on the backward measurement, 58.005. Now, we broke tape because we had too much of an elevation difference. And on the next line, 26.570 feet. And then we turned around and did the back. We got 26.572 feet. So I'm going to give you all, let's say, 5 minutes. Well, let me just give you also CA. So CA, there was less of an elevation change. And we could do the entire thing in one measurement. And what we got was 46.855 feet forward and 46.845 feet going backwards. So I'm going to give you all a few minutes here to calculate the average distances for all of those, the total distance for BC, and the precision for all of the measurements. So let's plug those numbers into our calculator, and then we'll move on to looking at our closure. All right, so while some of you are still running some calculations, just keep on running them, and let's just start going through a few of these. So what is the sum of the forward measurements on BC? $84,570. And thank you for anticipating. 84.577. All right. And then how about the precision on the first measurement on BC? Cool. 1 in 11,600. What about the second guy? $13,285. Awesome. And what about for the whole thing? One, yep. 12,082. Awesome. So our last one. So that also means that you must have calculated the averages correctly. These are good things that are easy to mess up. So if you're getting a wild precision like 1 in 2 or 1 in a million, you may have just plugged something into your calculator wrong when you were taking the average. All right, and what's the average for CA? This one again, we could probably, do in our heads. And the precision. $46.85. So looking at all of our lines that we taped, where did we do the worst in terms of precision?
CA.
CA, yeah. So we have the highest value there. So again, kind of like a sanity check. All of the other ones, we're getting like 1 foot of error in 2 miles or so. Whereas for CA, we're getting 1 foot of error in like 3/4 of a mile or 0.8 miles. So just kind of an idea of where we're at with these things.
I'm sorry, can I ask you one more question?
Yeah.
One more time, how do we calculate the precision on the lines where we broke the tape? Is it an average of 2 precisions, or is it like? Sorry.
So that's a great question.
I missed that part, sorry.
Is that when we break tape, we have to reach our specified precision for every single time that we break tape. So that would be this line here. We broke tape. We broke tape again here.
And
So-
how do we do the total line precision?
I'm getting to that.
Okay.
And then after that, we add them up, right? Because that is our calculation for line BC. And we use these three values in this row in order to calculate this precision. So we sum the forward, we sum the back, we have the average here. And we calculate the precision.
Okay, thank you. I got it.
Of course.
Thank you.
Any other questions on precision? All right. So the one last thing that we need to do for this lab is calculate some angles. So now we have line AB, the distance, BC, and CA. If we know the lengths of the sides of a triangle, we can calculate the angles. I already have the answer to this question written in the calculation section, but what law is that I have written? Law of cosines. Cool. So we are going to calculate angles A, B, and C. And what that's going to allow us to do is a mathematical check. We're going to mathematically, all of those angles should add up to be 180 degrees, the sum of the interior angles of a triangle. So, Kenny, I think that you pointed out on my lab videos, I had the sides incorrectly labeled. I'm sorry about that. So this is angle A at corner A. This is angle B at corner B. And this is angle C at corner C. So if we wanted to find angle A using the law of cosines, we know A, the distance A. What's the distance A? This is so what distance A in the law of cosines corresponds to this layout?
BC.
BC, exactly. So if you want to write a little note to yourself, this is A, and then angle B, what line of our triangle corresponds to B, the length little b?
CA.
So in this case, it would be AC. So little b is across from angle B. So we generally label these as the angle is the big letter, and then the distance is the small letter, and that distance is across the triangle from the angle. So that means that length AB would be our mathematical C. C would be between A and B. Yep, exactly. So if you need to add these little notes to your field book, I highly suggest it. You have to kind of make the the mental shift between, the math and what's actually occurring. So when you do this calculation, always fun. Remember, you have your, what do you call it? In radians? Ooh, that's wrong. Wow. In degrees, because we're working in degrees. Sorry, everyone. When we're doing these calculations. So let's first do angle A as a class, and then you can do B and C on your own time between now and Monday evening. I'll also stay afterwards if anyone wants a little bit of help with the math. But yeah, let's just do angle A together. So let's do the math together. So angle A. And you could do this in your field book on the next page, which you could just open up for calculations. So what is little a, the length A, equal to? Line BC, right? And what is the average distance on that line? Yep, 84.574 feet. B would be line AC. And little c would be line AB. And those are just going to be the average distances for each length. So we have 46.850 feet here and 121.012 feet for little c. Awesome. So when you're doing these calculations, just write out every variable in the math. Even though you don't have to show that in your field book, mentally, you want to just keep everything as clear as possible. What variable corresponds to what length and what is the measured length? Because now we can come in and say, well, if we're going to do angle A, the law of cosines that we want is A squared is equal to B squared plus C squared minus 2BC cosine A. So what's the algebraic breakdown of that? Well, you want that, we're after A. So cosine A is equal to what? B squared plus C squared minus A squared over 2BC. And A is just equal to the inverse cosine of that. Is this helpful for everyone, or is this, am I just going over math that everyone is super, super duper comfortable with? And is this just,
It was nice seeing it again as a reminder.
okay,
For
if this
the-
at least helps one person.
Yeah.
Okay, excellent. Cool. So that is how we find angle A. So I'm going to do the calculation in my calculator. If somebody else can plug some stuff into theirs, that would be great. All right, so we're getting some 31.32s. So I got 31.32, but we have 5 significant digits, so we can actually go even further to 324 degrees. All right. What's the one last step that we have to do to report our angle? How do we report angles in surveying? Convert the degrees, minutes, seconds. Now, some calculators have this function for you, but let's just go through really quickly how to do the actual conversion. So we already have our degrees. So it's 31 degrees. So we need to convert 0.324 degrees into minutes and seconds. So minutes, so 0.324 degrees. And what's our conversion factor? Yep, 1 degree for 50 minutes. This is the issue of using feet and minutes with the same symbol. So that is 19.44 minutes. And then seconds. Well, we have 19 minutes. And we have 0.44. So we want to take that 0.44. And again, conversion factor, 1 minute has 60 seconds. .4. So I'm kind of running out of space over here. So let's go back to our lab book, actually. Or does everyone have these notes? It's all being recorded, so they'll be somewhere. But it's easier to have them written down rather than going back through trying to look for them. Okay, so A, we said it has 31.324 degrees, which is equal to 31 degrees, 19 minutes, and 26.4 seconds. But that is too many significant digits. We only get 5. So what would be the degrees, minutes, seconds of this with 5 significant digits?
Yeah, dude.
What's that?
Oh, so wouldn't that be 31 degrees, 19 seconds, and 20, or 19 minutes and 26 seconds? We just rounded up.
So that would be 6 significant digits.
Oh, right. You're right. Yes.
Yeah,
I was
30.
doing it wrong. Thank you. Yeah.
19. Great. I'm going to leave the rest of the math to everyone else. So the other things that you need to do is after you calculate A, B, and C, you take the sum of the angles, you subtract 180, and that will give you and then the other thing you need to do is use the area formula using the size of your triangle to evaluate the area in terms of square feet and acres. So again, if anyone needs any help with that, we'll do it afterwards. Let's go to, or is there any other just kind of general questions about taping, calculations, etc., before we move on to differential leveling? All right, well, if you do, throw them in the chat. We will go over that afterwards. Okay, so lab 3 differential leveling. I'm going to leave it up to you to fill out the necessary requirements on the right-hand side of the page. You can use all the exact same information. Normally the taping would probably take you 2.5 hours, and it'd probably warm up, so you might change the weather, but other than that, everything is the same. So I'll leave that to you guys, or you all. All right, so let's just go through the data itself and the calculations. And if I can clear anything up, that would be good. So,
Kyle,
yep.
did you want to take a quick break and then have 2 separate videos for posting, one for lab 2 and then a separate one for lab 3?
You know, Kenny, that is an excellent suggestion, and let's do that. Let's give everyone, if you want 10 minutes, I can stop recording.